All right, so the recording of the session is started. And I will be uploading all these videos on a folder, in a folder on my Google Drive. And I think I have already shared the link of that folder with you guys. So I don't have to share the link again and again, because the link I have shared is not of a particular video. It's of the folder. So every week after the class, I will put the video in the same folder. So using the same link, you can access the video. Okay. So you know that the theory part will be covered by two teachers, myself, Dr. Mazhar Salim, and Dr. Safir Abbas. In last week, we discussed that what are the topics that I'll be covering and what are the topics that he will be covering. So I'll be mainly talking about beams, and in beams, I will be discussing shear force diagram and bending moment diagram. Okay, as long as I'm not writing anything, I can switch my camera. Okay, so we will be talking about beams together. We will be discussing shear force diagram and bending moment diagram in detail. First of all, we'll see that what these shear forces and bending moments are, how do we define them, and then how to calculate them, and then how to represent them on a diagram. And after this, our next main topic will be deflection calculation. Whenever we have a structure that is subjected to some external load, it exhibits some deformations or deflections. And as a structural engineer or as a civil engineer, it is important for us to determine that how much deflection is there. So in this semester, we will learn that how to calculate those deflections for beams. There are several different methods available for that. We will be discussing probably 3 different methods for deflection calculation. Okay. So as I said that we will be talking about beams all the semester. So first of all, it is important for us to understand that what a beam is. In last class, we talked about beams. So can anybody tell me what a beam is? Anyone?
Sir, can I?
Yes,
Okay.
sir. Can I?
Okay, 84, please go ahead.
Sir, beam is a structural member which is basically a load carrying member and it supports load. And it is it is most of the time the horizontal member, but it's not necessarily a horizontal member. It can be a vertical or inclined somehow.
Okay, that is right. That's correct. So beam is a structural member that is subjected to transverse loading. By transverse loading, I mean load that is perpendicular to longitudinal axis of the member. Means that if this is a member, now this is a beam. If I apply a load like this, let's say this load is 5 kilonewton. So this load is transverse load because it is acting perpendicular to the longitudinal axis of the member. And this, under the application of this load, shear force and bending moments are generated in the beam. We will discuss what shear forces and bending moments are. And as you mentioned, that beam is a structural member. So there are 2 types of members, structural members and architectural members. Structural members are the ones that take care of loading, means in simple words, these are load-bearing members. On the other hand, architectural members are there just for the sake of aesthetics. For example, false ceiling is an architectural member. It does not take care of any load. It is there just for the purpose of looks or beauty or aesthetics. So, but beam is not that type of member. Beam is a structural member and it is subjected to transverse loading, and under the application of transverse loading, shear force and bending moments are generated in the beam. And generally speaking, beams are horizontal. but this is not a necessary condition. A beam may be horizontal or it may be vertical, depending upon, or even inclined. Uh, uh, so the important thing is the nature of the applied loading and the forces which are generated in the member. Maybe for an architect, beams are always horizontal. Horizontal members are beams and vertical members are columns. But for civil engineers, it's not like that. For civil engineers, the behavior of any member is important. For example, for the same member, if I remove this vertical load, means the load along the load transversely acting to the member. If I remove this load and I apply load here and here, now this member will become will start behaving like a column, because columns are primarily subjected to axial loads. Okay, so this was the basic definition of beams. We talked about that in last class as well, but I wanted to give a quick review one more time. And then we have different types of supports. So can anybody let me know that what are different types of supports?
Yes, sir. Can I?
Yes, sir. Can I?
Okay, sure. The one who said, oh, okay, wait a minute. Or let me choose. Roll number 78. Roll number 78, are you there?
Yes, sir.
Okay, 78.
Yes, sir.
So can you tell us something about different types of supports?
Yes, sir. There are three types of sports: hinge sport, roller sport, and fixed sport. In hinge sport, it bears only one force. In fixed sport, it bears two forces, and in hinge sport, it bears three type of forces.
Fixed support bears two forces and hinge support bears three forces.
Yes, sir.
Okay.
No, sir.
No. Okay,
No,
then
sir.
what?
Sir,
Okay.
No, sir.
Hasham.
yes, sir. Sir, fixed bear three forces perpendicular, parallel to supporting for surface and moment of reaction.
And
In spot bears two perpendicular and parallel to supporting surface, and roller spot only perpendicular to supporting surface.
okay, that is right. So we have three types of supports. This support, this is the symbol of a hinge support. This is a hinge support. This one, okay, if I draw the first one, the simplest one at first. So this is roller support. It's roller, and this one is fixed support. So we have three types of supports: roller support, hinge support, and fixed support. And roller support can only generate one reaction. If I draw it using a different color. So roller support can only generate one reaction, which is perpendicular to the supporting surface. Now here is the supporting surface, and supporting surface is horizontal. So the reaction that roller support will generate will be perpendicular to that supporting surface. And in this case, it is vertical. Hinge support can generate two reactions. The supporting surface in hinge support, in this case, is horizontal. So one reaction is vertical and the other reaction is horizontal. So hinge support can generate two reactions. One reaction is parallel to supporting surface and the other reaction is perpendicular to supporting surface. And then we have fixed support. Fixed support can generate three reactions. So one reaction, two reactions, and three reactions. One of the reactions is vertical, one is horizontal, and one is perpendicular. So we can say that it is parallel to supporting surface and perpendicular to supporting surface and a movement. So it can resist a movement as well. These are three different types of supports. And one important thing to note here is that sometimes students define it that roller support is the one that can generate a vertical reaction. and hinge support is the one that can generate a vertical reaction and a horizontal reaction. In general, this is fine, but this statement is not true in all the cases because these supports may be provided in different orientations. For example, like here, this is true. This roller support will generate one vertical reaction, and this hinge support can generate one vertical reaction and one horizontal reaction. But in some cases, we provide supports in different orientations. For example, if for a member, let's say I have a frame structure. Frame structure is a combination of beams and columns. This vertical member here is a column, and this member is a beam. A roller support may be provided like this. Now, in this case, roller support can produce what reaction, what type of reaction, horizontal or vertical?
So horizontal.
In this case, roller support will generate horizontal reaction. Okay, just to make the structure stable, if I, let's say, add a support here as well. So in this case, roller support will generate a horizontal reaction because the supporting surface is vertical, so the reaction generated will be horizontal, perpendicular to the supporting surface. However, in this case, the supporting surface is horizontal, so the reaction generated will be vertical. And here, one vertical reaction will be generated and one horizontal reaction will be generated. So depending upon the orientation of the support, a roller support may generate a horizontal or vertical reaction. So defining a roller support as a support that can generate only vertical reaction is not the right way. It is not true in all the cases. So we define roller support as the one that can generate reaction perpendicular to the supporting surface. Hinge support is the one that can generate reaction parallel and perpendicular to supporting surface. And fixed support is the one that can generate reaction parallel to the supporting surface, perpendicular to the supporting surface, and a resisting movement that can be, let's say, labeled as M. We can call this, let's say, our vertical and our horizontal, right? So there are three types of supports. Everybody is clear about this? Any question about these types of supports? Anyone? Right now I cannot see you guys on Teams, so you can just interrupt me. You don't have to raise your hand. If anybody has any question, he can go ahead, he or she. Or I may ask someone. Registration number 92.
Yes, sir.
Okay, 92. Are you clear about these three types of supports?
Yes, sir.
Okay, so what is a fixed support?
Sir, fixed support has three reactions: horizontal, vertical, and rotational.
And rotational. Roller support?
Roller support have only one reaction, either vertical or horizontal, depending on the condition.
Okay, what condition? Depending upon what condition?
Sir, if it is horizontal to the beam or column, the reaction will be on the parallel to the axis.
Parallel to actually, the right way is to say it depends upon the orientation of the support and the orientation of the supporting surface. If the supporting surface is horizontal, in case of a roller support, the reaction will be vertical. So it will always be perpendicular to the supporting surface. If the supporting surface of a roller support is vertical, the reaction will be horizontal. Okay?
Yes, sir.
And similarly for hinge support, if one reaction is parallel to the supporting surface and other reaction is perpendicular to the supporting surface. So there are two reactions, and these supports are not just not always like either vertical or horizontal. Sometimes we have inclined members and inclined supports as well. For example, if we have a structure like this, might have a fixed support here, and we may have a hinge support here. Now in this case, the hinge support the hinge support has inclined orientation. So the two reactions generated will be like this. Ultimately, we can resolve these reactions into their horizontal and vertical components, but the loads that will be initially generated will be inclined. The reaction parallel to the supporting surface and perpendicular to the supporting surface. Okay, and here it will be like this. And one thing is that these we know that it will be parallel to the supporting surface or perpendicular to the supporting surface, but we don't exactly know that what will be their direction, whether this reaction will be leftwards or rightwards. Or if I say these are my axis, this is positive x direction and this is positive y direction, I do not know that whether this R horizontal will be along negative x-axis or along positive x-axis. I'm just hypothetically marking these directions. Their direction depends upon the orientation of the applied loading. There may be 2, 3, 5 or 10 different loads acting on the structure, and their algebraic sum will define that whether this RH will be along the positive x direction or along negative x direction. So if somebody watching this right now assumes that I actually know that whether it will be along negative x direction or positive, and I'm marking that accordingly, that's not true. At this point, I don't know. We don't know the applied loading or etc. Okay, everybody is clear about this?
Yes, sir.
All right. So if you are clear about these concepts, type 1 in the chat box. I'm looking at the chat right now. So type 1 in the chat box if you do not have any question. All right, I want to see a lot of ones. $75. You have a question? Type Q. Or is that a typo?
No, sir.
Okay. All right. So I hope this is clear to everyone. If not, you may ask me at any point. Okay. So after different types of supports, let's go to different types of. One clarity before jumping to different types of beams, that these three types that we have just covered, these are very distinct types of beams that we are saying that either a support is a hinge support or a roller support or a fixed support, but practically these types are not like that distinct. Like it is hard to find a perfectly fixed support that can resist the entire movement, or a support that is like truly roller. In only some of the cases the supports are very close to roller, otherwise they have the ability to generate some reaction parallel to the supporting surface as well because of the self weight of the structure. So as a beginner, and in theory we are studying or we are saying that the actual support conditions are very well defined, but in reality these systems are a bit more complicated. Okay, and how do we provide these supports like practically? For example, this type of beam is a simply supported beam. We are just going to talk about the types of beams now. Now how do we provide this type of or generate this type of end condition in real structures? What we do, let me show you that if we have a beam like this, so at one end, let's say at this one, this is a column on which the beam is resting, and this is another column, So what we do in order to practically provide these supporting conditions, we allow the beam to move in the horizontal direction here. Can you guys see this gap here that I have made in between? This hash part is column and then this part is beam. This beam, this is the column, right? So this gap allows the beam to move in this direction. So there is no reaction generated at this end, only vertical reaction. It is providing only vertical support. Whereas at this end, you can see that there is no gap between beam and column. So if I apply a horizontal load, this end will resist that horizontal load. And if I draw its free body diagram, this will be the free body diagram of this situation, this condition. We have a roller support at this end and we have a hinge support at this end. Okay, so this is how we provide these types of supports practically. Okay, a hinge support and a roller support. All right. So after this, now let's move to different types of beams. Types of beams. These types of beams are depending upon their end condition or their
Excuse me,
support.
sir.
Yes, please go ahead.
Sir, sorry to
No problem.
सर ये दोबारा पॉइंट एक्सप्लेन कर देंगे ये गैप वाला, ये थोड़ा बहुत समझ नहीं आया.
Okay.
बीम में
So,
गैप.
all right. What is a roller support? Roller support is the one that can generate reaction normal or perpendicular to the supporting surface only. It cannot generate a reaction parallel to the supporting surface. And on the other hand, hinge support is the one that can generate reaction perpendicular to the supporting surface as well as parallel to the supporting surface. So what I'm trying to show in this diagram is that how these supports are provided practically in real structures. Whenever we want to provide a hinge support, we provide a support in a way that it has a horizontal supporting surface and it has a vertical supporting surface, so that one reaction is generated here and one reaction is generated here. You see that if the beam tries to move in the horizontal direction, let's say in this direction, then this supporting surface will provide a reaction against that. Whereas on this side, if beam tries to move in the horizontal direction, in the rightward direction, the end of the column is not intact or in touch with the beam, so it will not generate any reaction. It will let the beam move. So no horizontal reaction will be generated, only vertical reaction will be generated here. So this diagram is trying to explain that how these roller and hinge supports are provided in real structures. This is the arrangement of a roller support. And this is the arrangement of a hinge support. Is that clear now?
सर अगर आपने ये लेफ्ट साइड यानी कि हिंज सपोर्ट को फिक्स करना हो तो आप क्या करेंगे?
For fixity, we will provide like, let me show this here. If this is a beam and I want to provide fixed support, I will make an arrangement something like this. This support is behaving like a fixed support.
सर इसमें रोटेशनल इफेक्ट कहां पर आएगा?
Rotational effect, because now this member is clamped like completely from the top as well as from the bottom, so the rotational effect will be generated here in the support. I've just shown it outside. The vertical reaction will be generated here, horizontal reaction will be generated here. So this column will not let the beam move either in vertical direction or in horizontal direction, or it will not let the beam rotate as well. So this type of arrangement for fixed support, this is for hinge support, and this is for roller support. Is that clear now?
Yes, sir. Thank you so much.
Okay, all right. So now let's move to types of beams. And these types of beams are with respect to supporting surfaces or end conditions. We use the term of end condition. These are the types of beams with respect to end conditions. Okay, so can anybody tell me some common types of beams?
Yes, sir. May I?
Okay, yes, sure.
Sir, the first one is simply supported beam.
Okay, what is, okay, first you can name them and then we'll talk about them.
Yes, sir. One is simply supported beam. One is
Okay.
cantilever beam.
Okay,
One is fixed ended,
all right,
and one is continuous beam.
right.
Sir, we
Okay.
discussed these in the introduction lecture.
Introduction lecture. Okay, that's good. That's good. So we have several types depending upon the end conditions. For example, this type of beam, which has a hinge support and a roller support. This type of beam is termed as simply supported beam. This is a simply supported beam. What is a simply supported beam? It's a beam that has a hinge support and a roller support. And one clarity is that these types of beams have nothing to do with the applied loading. This may be subjected to like a point load or a uniformly distributed load or a varying distributing load or any load. Whatever is the load acting on this beam will still remain as a simply supported beam. Okay, then we have another type, and that's termed as cantilever beam. Now, what is a cantilever beam? Cantilever beam has a fixed support. One support is fixed and the other end is free. So we have a beam that has one support as fixed and other end is free. So this type of beam is termed as cantilever beam. And what are the reactions that will be generated in this case? Hinge support, so 2 reactions. Roller support, 1 reaction. What will be the reactions in this case? Fixed support, so 1, 2, and 3 reactions. Okay, and then we have another type that is termed as an overhanging beam. An overhanging beam is a one that has one end projected beyond the support. Let me see. I see some movement on my teams. Is waiting in the lobby. Why waiting in the lobby? Shehzad 102. Okay, let me see. Is there? I have a few more students here, so I'm changing their status as attendee. All right, I'm going to take your attendance one more time. I will be keeping track of this thing, that how many students appeared at 8 o'clock and then how many of them were late. And if I see some habitual people, then it is going to have some consequences. Okay. All right. Okay, so we were talking about the types of beams. This type of beam is termed as overhanging beam. Now, what is an overhanging beam? In overhanging beam, either one or both ends of the beam are projected beyond the support. For example, here we see that in this case, in simply supported beam, both the extreme ends of the beams were supported. On the other hand, in case of overhang beam, one end has support at the extreme end, but the other extreme end does not have any support. We have a support here. So we will have one reaction here, another reaction here, and the third reaction here. So this type of beam is overhanging beam.
Sir,
And
can you draw a diagram of overhanging beam in columns or beams? मतलब सर उससे पता चले कि कैसे मतलब ये होता है.
no, in you mean like this?
Yes sir. सर ये
Okay.
सिर्फ जो हैंगिंग है इसको काइंडली शो कर दीजिए जो रोलर स्पोर्ट्स है आगे.
Okay, if I draw the hanging part, overhanging part, it will be like this. Column is here, and on this column, the beam is resting. So this is hinge support, this is a roller support, and this is the overhang part.
सर रोलर सपोर्ट मूवमेंट तो यहाँ पर नहीं आएगी जिस तरह ऊपर थी.
Okay, the first one. Okay, yeah. What were you asking? Please again.
सर रोलर सपोर्ट में आपने ऊपर वो मतलब गैप दिया था कि रोल करके एक्सपेंड वगैरह हो जाए. यहाँ पर ये फिक्स मतलब बिल्कुल साथ है.
The gap was on the vertical face. In this case, the gap is actually there. Actually, there is no vertical face of the column. So this entire side, it has a gap, right? So that gap was there to allow movement in the horizontal direction. And here again, you can see that we have only horizontal supporting surface here. Just like here, we have only one supporting surface, and that is horizontal. Similarly, here we have only one supporting surface, that is horizontal. So in the horizontal direction, if the beam tries to move due to any force or anything, the beam can move in the horizontal direction. So this support will act as a roller support.
Okay, sir.
All right. Okay. Yes. Who else was? Yes, please go ahead.
सर जो ओवरहैंगिंग बीम में सर जो रिएक्शन हमने जो सपोर्ट दी है वो हिंज सपोर्ट जो दी है इसकी जगह हम फिक्स सपोर्ट भी लगा सकते हैं.
Oh yes, hinge support. Yeah. Actually, the point is that there should be one overhanging part. The other support does not matter. Even instead of this hinge support, we might have a fixed support. You're right. Even if we have a fixed support here, this beam will still remain as an overhanging beam. Okay. Did you get it?
Okay, sir. Thank you.
All right.
Okay,
sir.
Yes.
सर ये जो ओवरहैंगिंग बीम है लाइक सर ये तो दो पार्ट्स में यहाँ पे डिवाइड हो रहा है. मतलब फर्स्ट साइड पे हमारे पास सिंपली सपोर्टेड आ गया और दूसरी साइड पे मतलब एक एंड हमारे पास फ्री है. तो सर ये तो मतलब स्ट्रक्चर से बीम बाहर नहीं चला जाएगा क्योंकि हम लोगों ने कॉलम पहले यूज कर लिया.
Actually, practically, we need this type of arrangement in some of cases. For example, in your houses, if you look at balconies, or if you look at the shades projected beyond your exterior face of your house, have you ever noticed that the shade that you project beyond the external wall of your house, that shade is basically an overhanging part? So this situation is exactly showing the shade of a house, or shade of a let's say a window or a door. So beyond the slab we project a part. So this part is outside the structure, but as long as it is properly designed, it does not matter. We see that every day. Okay.
सर ये जो शेड होता है वो मतलब बीम का ही पार्ट आगे आ रहा होता है.
Yes, actually it's the part of slab, precisely speaking. In some cases we have projected beams as well, but even slab, when you later on in your studies, when you will design slabs, you will see that slabs are also designed in a very similar way as that of beam. So either a beam projecting outwards or a slab projecting outwards. These are designed in a very similar way. So if you just see around, you will find some examples of these projected beams as well. Like for example, do you guys know the term pergola? That's a term commonly used in our construction. Those are beams that are used for basically architectural purposes. In terraces or in balconies, they have some projected beams. Those are, in some cases, overhang beams or cantilever beams. Okay.
Yes, sir. Clear.
सर मेरा एक क्वेश्चन
Yes.
था सर
Yes. Yes.
सर अगर आप कह रहे हैं ये स्लैब होगी सर तो रोलर फिर रोलर रहेगा नहीं क्योंकि ऊपर से भी सपोर्ट आ रही होगी इसको.
No, it depends that whether we have another story at the top or not. If we have another
first
story,
story, ground floor.
Yeah, if it's a ground floor, right, and there is nothing at the top, so it will be this type of arrangement. Okay, and if we have a column at the top as well, and again, as I said earlier, that theoretically we define these supports into three distinct types. That okay, one is roller support, one is hinge support, one is fixed support. But practically, these supports are not so distinct. Even if we have exactly the same arrangement, because of the self-weight of the structure, because the slab or beam will have significant self-weight, so it will generate some horizontal reaction here. Although that will be small, not as large as this end, but some horizontal reaction will be there. So strictly speaking, it will not be a roller support. But for analysis, for simplification, we will consider this as a roller support. When you will go in next semesters and you will be studying these things at a deeper level, at that stage you will realize that these types of supports that we are defining to be very distinct at this level practically are not that distinct. So your point is right that in some of the cases, or probably we can say that in all the cases, we might have some horizontal reaction as well at roller supports. That's true. Okay. But at this stage, we will not go into that depth. All right.
Sir, I
Okay.
have a question.
Oh yeah.
Sir,
Yes.
What if the beam is overhanging from the both sides?
Yes, it is possible. We have sometimes we use the term of single overhang for this type of overhang, and if we have an overhang on both the sides, let's say on this side as well, we use the term of double overhang. These are the terms sometimes used, but it doesn't matter. It may be single or double. Both are overhanging. Okay. So
कैंटिलीवर बीम को हम लोग ओवरहैंगिंग बीम कह सकते हैं?
No. Cantilever beam is cantilever. That's not overhang. That's different. Cantilever beam has a fixed support and the other end is free. Cantilever beam is the different type and overhang beam is a different type. Okay, after this, next, like another beam that somebody mentioned was fixed-ended beam. Fixed-ended beam is the one that has both ends as fixed. So this is fixed-ended. Fixed-ended beam. It has both ends as fixed. Another example is another type of beam is a continuous beam. Continuous beam. Now, what is a continuous beam? Continuous beam is the one that has more than one spans. The distance between two consecutive supports is termed as a span. So this is span 1 and this is span 2. Now, if you look at these like other beams, these ones, this has one span, this has one span. Like if we don't have any support at the other end, then we'll call this even for a cantilever beam, this is a span, termed as span. This beam has one span, overhang is not termed as a span. And this beam has one span, whereas this beam has two spans. So any beam that has more than one spans is termed as a continuous beam. the analysis of continuous beams is more complicated as compared to the analysis of simply supported beam or a cantilever beam. So we will not be covering the analysis of continuous beam here. Similarly, fixed-ended beams, we will not be covering them in this semester. How these beams are different with respect to analysis, we are going to talk about that just in a short while. I'll explain what is the difference. So this is continuous beam, and then we have another type. This is termed as propped cantilever beam. P-R-O-P-P-E-D. Propped cantilever. So this type of beam is termed as propped cantilever beam that has one fixed support and one roller support. So these are 6 common types of beams. There are other types of beams as well. If you see the literature, you might find other types as well, but these are 6 common types, and in your study, most of the time you will be dealing with any one of these beams. Okay, so everybody is clear about these types of beams?
Yes, sir.
Sir,
yes.
Sir, cantilever beam की practical example कोई एक दे दें.
Cantilever beam, like I said, pergolas are some architectural members that just project from the face of some building. In houses, you might have seen that, like the houses that are properly designed normally by architects, for example. Those houses have architectural members that are projecting outside of the face of the structure, and even in some of the cases when let's say the shade of a building is a bit long, sometimes we have to provide beams underneath them. For example, if we have a building that has that shade length is a bit long, then we provide a beam underneath that. In this view, that beam will appear like this. So this beam will be an example of a cantilever beam that is projecting out of a support. And now, as we are talking about these beams in detail, so I would advise you to see the structures around you more critically, and you will start noticing that there are examples of these types all around. And if you see any structure, you can just ponder upon that, and I try to identify those types of beams. If you are not clear about that, we can discuss about that in class as well. Okay. All right. Anybody having any other question?
Sir, I read somewhere that a beam should be completely in equilibrium if it has at least 3 reactions. Is it true?
Yes. A beam that is termed as the stability. Although that stability and determinacy is covered in in basic mechanics. I don't know. Did you guys talk about that in basic mechanics? What is stability and what is determinacy?
No, sir.
Okay, all right. Then I will explain that again here. We'll talk about that. Don't worry. Okay. All right. I see something in the chat box. What is the difference between propped cantilever and overhanging beam? In propped cantilever beam, you see here. Let me come back to my camera. In a cantilever beam, the other end of the beam, one end has fixed support and other end of the beam is free. Whereas in propped cantilever beam, one end has fixed support, whereas other end has a roller or a hinge support. So there is a clear difference between a cantilever beam and a propped cantilever beam. Is that clear? Umar Abidi? Okay, that's great. All right, so these were different types of beam. Now, one thing, as somebody pointed out about the stability and determinacy. So these first three types that I have mentioned here, the first three types in this row, these are determinate beams. These are determinate beams, and these three beams are indeterminate beams. Determinate beams and indeterminate beams. Now, what are determinate and indeterminate beams? Determinate beams are the ones. Yes, any question?
सर इक्विलिब्रियम तीन इक्वेशन है, तीन रिएक्शन है, तो डिटरमिनेट हो गया, और तीन से ज्यादा होगी तो इंडेटरमिनेट.
All right, yes. So okay, let's discuss that a bit in a bit more detail. Any beam that can be completely analyzed using three conditions of equilibrium is termed as a determinate beam, and any beam that cannot be analyzed using three conditions of equilibrium, that is termed as an indeterminate beam. And this is something true about a two-dimensional system. A two-dimensional system has everything in 2D plane. The structure is in 2D plane, all the applied loads are in 2D plane, and all the reactions are in the same plane. So all these beams that I have just drawn here are two-dimensional beams. Everything is in a two-dimensional plane. All right. So even if some loads are acting, those loads will be acting in the same plane. And what are the conditions of equilibrium for a two-dimensional system? The equations of equilibrium are sigma fx equal to 0, sigma fy equal to 0, and sigma mz equal to 0. This thing you have covered in your basic mechanics. So we have these three conditions of equilibrium. And in this case, x-axis is here, y-axis is here, and z-axis is out of plane axis. So if any structure can be analyzed using these three conditions of equilibrium, that structure is termed as a determinate structure. And if any structure cannot be analyzed using these three conditions of equilibrium, that structure is an indeterminate structure. Someone's mic is turned on.
सर आपकी आवाज मुझे
सर आपकी आवाज नहीं आ रही, बहुत डिस्टॉर्शन आ रहा है.
Because someone's mic is on. Sham's mic is on. Everyone, keep your mic turned off. If your mic is turned on, then there is a lot of noise. Okay? All right, something in the chat. What is mz? Mz is moment about z-axis. Like, okay, now let me change the camera view to explain what is mz. Okay, if we have this member here, let's say this is a beam, and this axis is the longitudinal axis of the member, right? And this axis is, let's say, x-axis, y-axis is vertical axis, and z-axis is out of plane axis. Okay, and if this member bends down, for example, instead of this pen, if I take the example of this paper, now if this member, if it bends down, this moment is about z-axis, because this axis, out of plane axis, is z-axis. Is z-axis. In out of plane direction. So this bending moment, or this moment, is termed as mz. So whenever, let's say, if let me draw it on a paper. So if I have, like, you guys would have studied beam analysis in basic mechanics, right? Have you guys studied that? Yes or no? Anybody? Yes. Okay, that's good. So in beam analysis, what we do, for example, I apply a load here and I want to calculate these two reactions, right? So what I'll do, if I say that this point is A and this point is B, and this load is, let's say, 5 kilonewton, this span is also 5 meter, supposedly, then I will take sum of moment about point A, sigma MA equal to 0. I'm saying this MA because I'm taking moment about point A, but in terms of axis, whether that sum of moment about point A is about x-axis or y-axis or z-axis, it is about out of plane axis, about this axis. Because the rotation that's going to take place will be about out of plane axis. So mz is the moment about out of plane axis. How this equation will be applied, how to calculate the reaction, we are going to see that later on. But today, right now, if you want to ask that, what do we mean by mz? So, and yes, one more clarity. When I say sigma ma equal to 0 or sigma or ma, what do we mean by ma? By ma, I mean moment about an axis which passes through point A and is perpendicular to the plane, xy plane. Like everything is in this plane. This is x and this is y and this is z. So z is basically out of plane. Z is like this. Okay, x is rightward, y is upward, and z is outwards. And when I say MA, I mean movement about an axis which is perpendicular to the XY plane and it passes through point A. So that is MZ. Okay, now let's come back to our beam types. So determinate beams and indeterminate beams, when we have an arrangement in which beam can be completely analyzed using these three conditions of equilibrium, we call that beam as a determinate beam. And if a beam cannot be analyzed using three conditions of equilibrium, that is an indeterminate beam. For example, here we have both ends fixed. Both ends fixed mean how many reactions will be there? 1, 2,
6.
3. 6, that's right. 4, 5 and 6. So there will be 6 reactions. If there are 6 reactions and we have just 3 conditions of equilibrium to analyze the system, it means that this system cannot be analyzed using just by using equations of equilibrium. We need some other system to analyze. We need some other way to analyze the system. So this type of arrangement, this type of beam is an indeterminate beam. Now let's move to this continuous beam. How many reactions will be there? 1 reaction, 2 reaction, 3 reaction, and 4 reactions, right? 4 reactions, 3 conditions of equilibrium. This beam is an indeterminate beam. How many reactions are there? 1,
4.
2, 3, 4. 4 reactions are there, and how many conditions? 3 conditions of equilibrium. So this beam cannot be analyzed using 3 conditions of equilibrium. Therefore, this beam is also an example of indeterminate beam. So this is how we decide whether a beam is determinate or indeterminate. And with this concept, I can also talk about the degree of indeterminacy. Have you guys ever heard about this term, degree of indeterminacy?
No, sir.
Okay. So degree of indeterminacy is the difference between the number of reactions and the conditions of equilibrium. The number of reactions that can be generated in this case, for example, how many reactions are generated for a simply supported case? 3 reactions. And how many conditions of equilibrium are there? 3 conditions of equilibrium. So degree of indeterminacy, if I say that as DOI, degree of indeterminacy, it is termed as
0.
degree of indeterminacy. Indeterminacy. So degree of indeterminacy for a simply supported beam is 3 minus 3 equal to 0. Degree of indeterminacy for a cantilever beam is 3 minus 3 equal to 0. Degree of indeterminacy for an overhanging beam is 3 minus 3 equal to 0. That is why these three beams are determinate beam, because their degree of indeterminacy is 0. What about the degree of indeterminacy of a fixed-ended beam? Degree of indeterminacy. How many reactions? 6 reactions. How many equations of equilibrium? 3. So degree of indeterminacy is 3. For a fixed-ended beam, degree of indeterminacy is 3. What about this example of a continuous beam? Degree of indeterminacy is 4. How many reactions? 4 reactions. 1, 2, 3, 4. How many equations of equilibrium? 3. So degree of indeterminacy is 1. How many reactions are there for a propped cantilever beam? 1, 2, 3, 4. So if you want to calculate degree of indeterminacy is 3 equal to 1. So degree of indeterminacy basically tells us that how many more conditions of or how many more relationships or how many more equations do we need to analyze the system. So degree of indeterminacy is 3, degree of indeterminacy is 1, degree of indeterminacy is 1. In this semester, we will be talking about determinate structures all the time. So we will not need to calculate the degree of indeterminacy. But in future, in next semester or in next to next semester, when you will be dealing with indeterminate structure, you will have to calculate the degree of indeterminacy in order to understand that how many more relationships are required in order to solve the system. Okay, sir, what about the reactions are less than 3? Okay, we are going to talk about that. What if the reactions are you said less than 3? Yeah, reactions are less than 3. Now, when the reactions are less than 3, then there is no question of determinacy or indeterminacy. Then there is question of stability or instability. If there are 2 reactions, let's say, that structure will still be a determinate structure because, for example, if I draw a beam like this. Now this beam has 2 roller supports. How many reactions it can generate? It can generate 2 reactions only. So this is a determinate beam. This is a determinate beam. But there is another question that is about stability. There are 2 questions. Determinacy tells us that whether this can be analyzed using conditions of equilibrium or not. So that's something else. Other question is about the stability, that whether this structure is stable or not. So for stability, we need at least 3 reactions. For stability, we need, for a stable structure, there should be 2 conditions, at least 3 reactions, and okay, all right, so there should be at least 3 reactions, and those 3 reactions, all of those 3 reactions should not be parallel to each other. This is symbol for parallelism. So all these reactions, all the reactions should not be parallel to each other. We'll see under what condition this statement is important. Now this beam, what do you think? Is this beam a stable beam or not?
No.
No, sir.
This beam is not a stable beam. Why? Because if let's say I apply an inclined load on this beam, inclined load has two components. One is vertical component and other is horizontal component. This horizontal component will have the tendency to slide the beam in horizontal direction, and our supporting system cannot resist that horizontal reaction. If we apply a horizontal load, this beam will be slided off the support because both the supports are roller support. In contrast to that, if I have a simply supported beam that has one hinge support and one roller support, if I apply an inclined load on this beam having one vertical component and one horizontal component, this beam is still stable. We have a horizontal force here and we have a horizontal, we have a support that can generate horizontal reaction. So ultimately this structure will be a stable structure. But this structure is an unstable structure. Okay, so these, whenever we are analyzing or we are studying any structure, we have to check its like stability as well as determinacy. Whether a structure is a determinate structure or indeterminate structure, that is actually not a problem. That like an indeterminate structure is still safe, and actually it is even more safe. So the only thing is that we need some sophisticated method to analyze that structure. But if a structure is unstable, then that's a problem. Structure must be stable. If an unstable, it is unsafe structure. Now, I gave you two conditions. It should have at least 3 reactions and all the reactions should not be parallel to each other. Why I said that? Let me give you an example. Because sometimes students assume that if any structure has 3 structures, that is a stable structure. But that is not true in all the cases. For example, if we have a continuous beam like this. Now this is a continuous beam and it can have 3 reactions. But is it a stable structure?
No, sir. So
No,
these are
this
parallel
structure,
antenna.
exactly. All of them are parallel to each other. So if I apply an inclined load on this structure, having a vertical component and a horizontal component, this structure will simply slide off the support. So this is an unstable structure. So at the same time, this is a determinate structure. Or actually, even this is not a determinate structure as well. Let's not go into that discussion. That will, at this point, probably it is difficult to understand. This structure is not even determinate, but just let's forget about that. What I want to highlight here is about its stability, that this structure is an unstable structure. So as a civil engineer, whenever we design structure, we make sure that it should be stable. If it's unstable, then this is the problem. We have to make it stable somehow by changing the support conditions. Whereas as far as the determinacy and indeterminacy is concerned, that is not a problem, or you may say that that is a problem just as the analysis is concerned. So if it is determinates is easier to analyze. If it is indeterminate, it is relatively difficult to analyze. But it's not that it is unseen. Okay. So everybody's clear about this. Somebody's mic is turned on. Make sure your mic is turned off. Okay.
Yes, sir, I have a question.
All right. Yes, please go ahead.
सर ये जो डिटर्मिनेट और आपने बताया कि लाइक अभी 3 सपोर्ट्स है हमारे पास और ये स्ट्रक्चर डिटर्मिनेट था, तो सर इसके लिए सिर्फ जो वो डिग्री होती है यानी जो अननोन्स होते हैं वो 0 होनी चाहिए, ये मतलब सिर्फ कंडीशन है डिटर्मिनेट और इंडिटर्मिनेट की?
That is the condition, but okay.
Can I answer that, sir?
Sham, just wait. Let me just respond to him. Turn off your mic. Okay. Actually, in case of beams, if we if we have like, let me see how to explain that why the structure is unstable. Oh, why the structure is indeterminate. In this case, if we have an inclined load, there will be a horizontal force, but there will be no horizontal reaction. But the conditions of equilibrium that we have with us, those conditions of equilibrium are sigma fx equal to 0, sigma fy equal to 0, and sigma mz equal to 0. Although we have three conditions of equilibrium, and somebody may say that there are three conditions of equilibrium and there are just three unknowns. Let's say I call this point as A, this is B, and this is C. So this is RA, this is RB, and this is RC. So there are three conditions of equilibrium and there are three reactions. So this structure should be determinate. But actually, as I said, that this is not determinate. Why did I say that? Because we can apply sigma fy equal to 0 and we will get some relationship between known and unknown parameters. Similarly, we can apply sigma mz equal to 0 and we will get another relationship. But what about sigma fx equal to 0? If I apply sigma fx equal to 0 on this structure, I will get 0 is equal to 0. I will not get a relationship between known and unknown parameters. So if I do not get a relationship between known and unknown parameters, then this will not help me in analyzing the system, and ultimately I will just end up with two conditions of equilibrium and three unknowns. That will make the system as an indeterminate system. That's why I said this is indeterminate. But at this point, let's keep it simple. Even if you are not 100% clear about this, we can just leave that for future discussion. When we will be analyzing more and more beams, you will become more clear about this. Okay. At this point, you can just take my words that this is an indeterminate structure. Okay.
Yes. Thank you so much.
All right. Harsham, you wanted to ask something?
मतलब कि सर स्टेबल के लिए मतलब कि तीन रिएक्शंस होना जरूरी नहीं है. जैसे ये लास्ट एग्जांपल थी, इसमें तीन रिएक्शन थे, तो स्टेबल नहीं है.
No, there are two conditions. At least three reactions, and the second condition is all those reactions should not be parallel to each other. Whenever both these conditions will satisfy, that structure will be a stable structure. Okay.
Yes, sir.
All right, Hasham, did you want to ask something?
No, sir. मेरे भी mind में ये था, आपने answer कर दिया.
यही था. Okay, that's fine. All right. So we have now discussed the.
Sir,
Okay.
I have a question.
All right, please go ahead.
Sir, double overhanging जो beam है, sir वो determinate होगा?
Yeah, it depends upon the supporting condition. Now, what is a double overhanging beam? If I have a double overhang, this is what we call a double overhang. How many reactions will be generated? One reaction here, second reaction here, and third reaction here. There are three reactions and they are not, like all of them are not parallel to each other. So this beam is stable as well as determinate.
Sir, double overhanging beam में hinge support आएगी start में?
Yeah, there can be hinge support. Yes, sure. In fact, there would be a hinge support. There would not be a fixed support.
Structural diagram. Sir, इसकी structural diagram बना सकते हैं sir? ये field में होती है.
इसकी structural
double overhanging beam.
All right, now I got your point. What you want to ask? That in case of a double overhang beam, you are saying that how to generate this type of support in case of a double overhang beam. In that case,
yes, sir.
Like that would be the case when even the horizontal reaction will be generated with the like through the horizontal surface due to the friction between the supporting surface. There will not be this edge present there. That would be the case when we, in some of the cases, for example, in case of bridges, we actually place a roller under the bridge. Yes, this brings another important point in my mind is that sometimes students think that if I'm saying the support is a roller support, so students assume that there would be an actual roller in the structure placed under the beam. So in buildings or in most of the cases, maybe in 99% cases, that's not the case. When I say beam has a roller support, it does not mean that there is an actual physical roller or a sphere or a ball type thing present under the beam. But in some of the cases, in case of bridges, where we want to allow expansion of the bridge, minimum resistance, we actually place rollers under the bridges. Okay, so in that case, the physical rollers are there. So those physical rollers will provide the roller support and the hinge support in case of, if it's a double overhang beam, the horizontal surface, the friction between the horizontal surface, the horizontal supporting surface between the beam and the column will generate horizontal reaction. In that case, this vertical face will not be there. Okay.
एक्सक्यूज मी सर.
Yes.
सर ये भी हमने बताया कि ब्रिज के एंड पे हम रोलर सपोर्ट रखते हैं, तो सर वो मतलब क्यों रखते हैं? एक्सपेंशन के लिए कि अगर मतलब एक्सपैंड हो तो?
Yes, because there are a lot of steel bridges and steel undergoes significant expansion in summer. When the temperature is high, steel expands significantly. In this course, most probably Dr. Safir will talk about thermal stresses as well with you guys. So when we have whenever steel bar undergo excessive heating, they are the thermal stresses or expansion is there. So in order to allow the structure to expand, we provide real roller under steel bridges, and that is the case where we have actual rollers under the beams. Otherwise, in buildings, we do not have those actual rollers. Okay.
Yes, sir.
All right. So let's come back to our discussion. So we have talked about the different supports and different types of beams. Now let's talk about different beam shapes. In this, when we will be talking about shear force and bending moment, we will not be concerned about the shape of the cross section. But when you will be talking about stresses, those which we will cover with Dr. Safir, and when we will talk about deflections, in those we will be concerned about the cross-sectional shape of the beam. So if I just tell you about different cross-sectional shapes, you guys have studied drawing, so you know what a cross-section is, right? So if we want to see the cross-sectional shape of a beam, most common one in concrete is rectangular. I hope all of you guys would have seen rectangular beams. Beams are the components projected below the slab, right? So most of the time concrete beams are rectangular. Then we have T-shaped beams as well. These are more common in steel. The cross-sectional shape is like T. We have, in common language, we call it I shape, but in engineering, we call it like W section. You will learn that thing later on in steel structures. So sometimes we have T shape and sometimes we have I shape members. This vertical member is termed as web of I section, WEB, and this part is termed as flange. This is also a flange of I section. This is flange of T section. This is web of T section. This is also termed as web. So these are some common cross-sectional shapes. Sometimes we provide box shape as well. Hollow box. The hashed portion is solid. This part is hollow. And in steel, sometimes we provide channel section or C section. So these are different cross-sectional shapes that we provide in case of beams. There might be some other shapes as well. Sometimes we provide circular sections as well, but those are normally for columns, not for beams. So let's leave this because it's not common for beam. Forget about this. So this is rectangular section, T section. For now, you may call it I section, but precisely this is W section. This is box section, and this is C section or channel section. So these are different cross-sectional shapes.
Sir, L section nahi hota?
Oh, L section, yes, that's true. L section is also there. L section bhi hota hai. You're right. We also provide L section sometimes. L section is a bit more complicated to analyze. Probably in this semester we will not be considering any L section beam, but you are right that practically we provide L section beams as well. Okay, so these were different cross-sectional shapes. Now let's talk about different types of loads as well. Although you guys are already familiar with that, but in this class I want to give you a quick review of all these basic things. So can anybody tell me about types of loads?
Transverse, axial.
Transverse load, okay, all right. I was actually talking about like with respect to their distribution.
So uniformly
Yes, sir, point
distributed.
load, uniform load,
Point load, uniformly
variable.
distributed load, and varyingly distributed load. So what is a point load? Uniformly distributed load, okay. If I have a beam like this and there is a load like this, so this load is a point load. This is a point load. Maybe it may be 5 kilonewton, let's say, as an example. Okay, and other type is uniformly distributed load. There are two ways to show uniformly distributed load. If you look at books, they show uniformly distributed load like this. Okay, so this is UDL, uniformly distributed load. Another symbol that is used for UDL, because whenever we are doing like solving something manually, so just for quick representation, we show it like this. That is another way of showing UDL. Both of them means UDL, and then we the intensity is given, okay, that this is 5 kilonewton per meter, supposedly. Okay, and how do we calculate the total weight in this case? It is equal to the magnitude of the area of this rectangle. 5 kilonewton is this ordinate, and this dimension is, let's say, I call it like L, span. Normally for span we use the symbol L, right? So if I want to calculate how much is the total area, let's say I call this omega. So the magnitude of the resultant, if I show it with a different color here. So the resultant, this load, resultant of this load will be acting at the center, and it will be omega L. For analysis, we will, in order to calculate how much is the total load and where is it acting, it will be acting at the center and magnitude omega L. And then third is VDL. VDL is shown like this. This ordinate is omega, this span is L. So the resultant of this load will be acting it will be acting here. If the total is L, this will be 2L by 3 and this will be L by 3, and the resultant will be equal to the area of this triangle, that is omega L by 2. So these are three types of loads that we will be dealing with: a point load, a uniformly distributed load, a varyingly distributed load. This is abbreviated as VDL, varyingly distributed load. And
सर
practically
WL का concept repeat कर देंगे एक दफा.
omega L, that is the area of this rectangle, and this is the magnitude of total magnitude of the load. W is the intensity, how much load is acting per kilonewton per meter, and span is in terms of meters, let's say. So WL is the resultant. This is resultant. And this is also resultant.
सर ये तो
This
एरिया
is
का
result-
फॉर्मूला था ना, for
Exactly,
rectangle and
yes.
for triangle.
Yes, that's true. These are the formulas for area. So the total magnitude of load is equal to the rectangle of this UDL, and in case of triangle or VDL, the total magnitude of load is equal to the area of the triangle.
Okay.
Okay, right? And practically these loads may be present, like if we have a beam and there is a column resting on the beam, then that is the example of a point load. If we have a wall over a beam, that is an example of a UDL, sorry, uniformly distributed load. And let's say we have a wall whose length is changing throughout the beam. We have a wall on top of the beam, or we have some sand, let's say, or any material whose height is changing along the length of the member, then that will give us a VDL. Okay. So these are the three types of loads that will be we will be dealing with.
Sir?
Yes, please go ahead.
Sir, kindly 2L over 3 और L over 3 को explain कर दो.
The resultant of a VDL, okay, the resultant of a VDL passes through the centroid of the triangle of the VDL. So this VDL is making a triangle, right? So the resultant of this VDL will pass through the centroid of the triangle. And what is the location of centroid of triangle? From the vertical side, it is L by 3, and from this side where the ordinate is 0, it is 2L by 3. L is the total span. In basic mechanics, you would have studied the geometrical properties of areas. Have you guys studied that? The geometrical properties of areas. Anyone? Did you guys study that?
Sir, lab में किया था थोड़ा सा.
Lab में किया था.
Sir, lab में थोड़ा सा.
Okay, what is the location of centroid of a rectangle? If this dimension is L, so it will be at L by 2. I did not mark it, I just somehow assumed to be understood, but I should have marked that. This is L by 2. The magnitude of the resultant is equal to the area of the rectangle, omega L, and the location of the resultant is L by 2. That is the location of centroid. Similarly here, the magnitude of the resultant is omega L by 2. That's the area of the triangle. And the location of the resultant will be L by this side and 2L by 3 from this side. That is the location of the centroid. Is that clear now?
Yes, sir.
All right.
Sir, इसमें sir,
yes.
Sir, उसमें जो आपने ये W शो किया हुआ है और L शो किया हुआ है, इनको मल्टीप्लाई कराने से हमारे पास रिजल्टेंट आ गया. तो क्या इसमें भी हमने W को L by 3 मल्टीप्लाई बाय 2L over 3 से करवाया है? क्योंकि
नहीं, इस केस में we have just multiplied this W or omega with L and divided by 2. We are calculating the area of this triangle. Just forget about this thing. When you are calculating the magnitude of the resultant, forget about L by 3 or 2L by 3. Just calculate the area of the triangle. Omega is the vertical dimension, L is the horizontal dimension. You may say this is perpendicular and this is base of the triangle. So perpendicular into base divided by 2 is the area. That will give you magnitude of the resultant. And then when it comes to location of the resultant, then you will see that, okay, from this end it will be 2L by 3 and from this end it will be L by 3. Is it clear now?
Yes, sir.
All
Yes,
right.
sir.
Okay, that is great. So these are different types of loads that we will be dealing with. Sometimes the structure are also subjected to point movements. The point movement is shown like this. This is called as point movement. When we will start solving the numerical problems, we will see how to deal with point movement. But this is another type of load that we will have to deal with. That's why I thought it's important to point out. And when I say load, I mean both forces as well as movements. Both are loads for us. Okay. This is a force and this is a movement. And when I say load, both forces and movements are present in the term load. Okay. So these are different types of loads. Then there are some other basic terminologies that you already know. For example, longitudinal axis. What do we mean by a longitudinal axis? Longitudinal axis of the member. Longitudinal axis. The longitudinal axis of the member is along the length and it passes through the cross section of the centroid. For example, if I say this is a beam, if this is a beam, so here is its longitudinal axis. This axis is longitudinal axis. It runs along the length of the member, and if I draw its cross section, this is a centroid. So longitudinal axis passes through the centroid. If I say that this is section 1-1, section 1-1, so this is the centroid of the section, and longitudinal axis passes through this centroid of the section. Okay. Whenever we solve the members, we solve the beams, we draw, normally we just draw the longitudinal axis of the member. For example, in several of the cases you have already seen that I did not draw the entire thickness of the or entire depth of the beam. I just drew the longitudinal axis of the member. Okay. So this is a term that we will be using frequently. So you should be clear that this is longitudinal axis of the member. All right. Then shear force. Okay, I said that in this semester we will be talking about shear force and bending moment like a lot. So let's see, what do we mean by shear force and bending moment? Do you guys already have an idea about that?
Sir,
What is the shear force?
Sir,
बस कर दें? क्यों क्या हुआ?
सर 1 घंटा 42 मिनट कंटिन्यूअसली हम आपके सारे कॉन्सेप्ट्स लिए जा रहे हैं सर, अब मतलब ज़्यादा ओवर हो जाएगा.
Concepts आप लिए जा रहे हैं, ओवर हो जाएगा, but we have like 2 hours for this. Okay, but what we can do from what we can do from next time, we will have a break after an hour. Okay, like we'll have a break, 10 minutes break from next class. But today I thought I really knew, so I did not give you break. But from next time, just remind me after 50 minutes or an hour, we will have a break for 10 minutes. Okay, but today these are basic things, so let's just cover them so that in next class we can just right away jump to our main article. Okay, so shear force. Do you guys have any idea about shear force?
यस सर।
Okay, what is that?
सर जब मतलब किसी भी बीम पे हम लोड अप्लाई करते हैं ना, तो उस बीम के अंदर सर इंटरनल फोर्सेस डेवलप होती हैं। तो सर मतलब जो डाउनवर्ड एक्ट कर रही होती हैं फोर्सेस, ठीक है सर, वो मतलब शेयर फोर्स होती हैं, और जो नॉर्मल उसकी एक्ट कर रही होती हैं वो मोमेंट कॉज करती हैं। तो सर जो मतलब डाउनवर्ड एक्ट कर रही होती हैं फोर्सेस, उनको शेयर फोर्सेस कहते हैं, जो स्ट्रेस प्रोड्यूस करती हैं उसके अंदर।
जो स्ट्रेस प्रोड्यूस करती है। Okay, ये जो नॉर्मल फोर्सेस, the thing that you pointed out about normal forces, we'll see that later on, but what is a shear force? Simple definition is shear force is the one that tends to slide two parts of a section against each other. So if we have a member, if we have a beam, okay, does anybody else want to say something? All right, so if this is a beam, this is actually a single beam, we have a force that is trying to slide these two sections against each other. Let me just change the camera. So if we have a horizontal member, a beam, and there is a force that is trying to slide two cross sections against each other, that force is termed as shear force. And shear force is an internal force that is generated in the beam as a result of the applied. Okay, I got a reminder. Due to the applied loading. For example, we have a beam, and on that beam, external forces acting transverse. Transverse means perpendicular to the longitudinal axis. This is a longitudinal axis. So a force that is acting here, vertical force in this case, that force is transverse force. So under the application of this transverse force, two types of internal forces are generated, and one of them is shear force. Shear force has a tendency to slide the cross sections against each other, just the way I have shown it here in the diagram, that the cross section has a tendency, the sliding tendency. So the force that tends to slide two parts of a cross section against each other, that force is termed as shear force. And there are two types of shear forces, or you may say there are two cases of shear forces. This type of shear force is termed as positive shear force. Positive shear force, in which left part of the section moves upward and right part of the section moves downward. This is positive shear. And there is then second case in which left part of the section has a tendency to move in the downward direction, and the right part of the section has a tendency to move in the upward direction. This is termed as negative shear. We will be using these terminologies, like we will be dealing with shear force all the time in this coursework, especially the discussion with me, and positive shear force and negative shear force. We will see how to calculate these forces later on, but at this point you should be clear about that what is a shear force. Shear force, I repeat, is a force that has the tendency to slide two parts of a section against each other. So that force is shear force. Then the next important basic concept is bending moment. Bending moment, what is termed as, now what is bending moment?
सर shear force के नतीजे में जो मोमेंट पैदा होता है,
जो मोमेंट, it is not due to the shear force, like it is due to the applied loading. When we apply transverse load on a member, then there are two results of those of that externally applied loading. If I talk about internal forces, so there are two internal forces generated in the member, in the beam, and those, one of them is shear force and other is bending moment. For example, if I have a beam like this and I apply a force in the downward direction, this will cause the beam to bend like this. And this bending, if the beam bends like this is called as sagging. This type of bending is termed as sagging, and then there is other type. If I have a similar beam, but let's say I apply load in the upward direction, this beam will bend like this, and this is termed as hogging. So this force and this force, these two are transverse forces, and this deflection or this type of movement is termed as sagging, and this is termed as hogging. Our sign convention will be, we take sagging as positive and we take hogging as negative. How do we incorporate this positive shear, positive movement and negative movement? We'll talk about that when we will start our discussion about calculation of shear force and bending moment. Okay, at this point you should be clear about this, that what do we mean by sagging and what do we mean by hogging. Sagging will be positive, hogging will be negative. What is positive shear and what is negative shear, and what is, if we how can we define simple movement? Is the what is the definition of simple movement? Movement is just the rotational effect of force. Whenever we have a force that has the tendency to produce rotation, that rotational effect is termed as movement. You guys have already studied movement in detail in basic mechanics. In this semester, we will be mainly focusing on bending movement. In fact, the discussion between me and you guys will be about bending movement. Dr. Safir will also discuss twisting movement. So bending movement is something that has the tendency to bend the member. If I have this member and I have force acting here, that force will tend to bend the member. This movement is termed as bending movement. And what is twisting movement, just for your clarity, if I have a member like this and I try to rotate it like this, this is again rotation, but this rotation is not trying to bend the member. So this rotational effect is termed as twisting movement. This is twisting movement, and this is bending movement. All right. So our discussion at this point will be about bending movement, not twisting movement. Is everybody clear about this? Anybody having any question about bending movement or shear force or anything that we discussed today? Okay, I can see your team screen now. So if anybody has any question, he or she can raise his hand.
Sir,
Yes, 84.
सर किसी बीम के अंदर सैगिंग और हॉगिंग दोनों हो सकते हैं कि हमेशा एक ही मूवमेंट प्रोड्यूस होगा?
No, a beam can partly sag and partly hog. This will happen, right? So actually in a lot of cases this happens, that partly the beam is sagging, partly it is hogging. We will see that. We will see several examples and we will come across such situations.
Okay, sir.
Okay. All right. Any other question? All these concepts that we have discussed today are very basic and very important. And these concepts, like, you will probably never be able to get rid of these concepts. These concepts will go along with you throughout your academic life and most probably your professional life as well. Shear force, bending moment, what are different cross-sectional shapes, and the different types of beams, and what is a beam. All these things you will have to apply, like, probably on a daily basis. So it's very important that you should be very clear about that. So today we just got a review of these things. In next class, we will be solving some problems regarding shear force and bending moment. And at that stage, when we will be solving the numericals, you guys will be able to develop better understanding about these concepts as well. Okay. So at this point, notes. Oh, these are like kind of not very clean notes. Do you guys want these? These are like, I expect you guys to note the lecture with me, and the video is also with you. So I will upload. We have recorded this session, and I will upload this session. So everything that I have written on paper, that will be with you in the video form. Okay. So you can just pause the video at any stage and you can see that. And I would strongly recommend you guys to keep on making notes, because you understand better if you keep on writing down the things. Okay?
Excuse me, sir.
Yes.
सर कोई बुक डाउनलोड वगैरह करनी है इसके लिए रेकमेंड कर दें.
Okay, I will provide you a book. I will share link of a book. It is R.C. Hibbeler. That's a good book that's followed internationally. So I recommend you guys to follow that book, and I will share the link of that book with you guys. Okay.
Okay, sir.
All right. So at this point, let me take your attendance one more time, just to see that later on, just for record. Okay, so at this point, we will conclude this meeting. I hope I see you guys next week, inshallah. Okay, Allah Hafiz.
कल हमारा लेक्चर है.
कल आपका लेक्चर डॉक्टर सफीर के साथ होगा. For the initial part of the semester, I will be taking 2 hours classes, and Dr. Safir will be taking 1 hour classes. And later in the semester, we will switch. Okay, so your lecture tomorrow will be with Dr. Safir. Okay.
Sir?
Yes.
Sir?
Yes. 71. Go ahead.
सर पहले मेरा नेट आ रहा था 8 बजे, फिर एकदम से चला गया, वो ट्रांसफार्मर ट्रिप हो गया था सर, वो 9 बजे दोबारा आया, तो सर काइंडली अटेंडेंस मार्क कर लीजिएगा.
Okay, I'm marking your class attendance again, and I will see that how many of you were present at different stages in the class. Okay, now I need to start preparing for the next classes starting at 10 a.m. So I'll be leaving. Allah Hafiz.